if you'd like to subscribe to our list and then receive announcements for the future talks, then please follow these instructions on the chat. You can either send us an email with the subject webinar or text via WhatsApp the word webinar to this number, and you're going to be added to the distribution list. Thanks a lot.
Okay, so we may start. Good afternoon, everybody. Welcome.
Tell me if you can see my screen.
Okay.
Yes.
Yes, yes.
Perfect.
Ah, the title is there. Okay.
Yeah.
So it's a great pleasure to introduce Professor Adrián Andrada from Universidad Nacional de Córdoba, Argentina, and the Institute CIEM from CONICET, who will talk about abelian almost contact structures and connections with skew-symmetric torsion.
Okay, well, thank you very much. Thank you very much for the kind invitation to give this seminar. And this is my first time giving a talk like this. I hope that I can do it well. First of all, I would like to say that this is a joint work with Giulia Dileo from Bari in Italy. And I have to say that I'm sorry that I forgot to mention her in the abstract that I sent to this seminar. So I'm very sorry. But well, here, everything that I will show here is a joint work with Giulia. Okay, so the contents of the talk. First, we will give some preliminaries on abelian complex structures on Lie groups, and in particular, their relations with hyperKähler with torsion geometry. And then we will try to define an analogous notion in the case of odd-dimensional manifolds. In this case, we will define what we call abelian almost contact structures, always on Lie groups and Lie algebras. We will see some properties of these structures, and then we will move to the case of abelian almost three contact structures. So this is a manifold which admits three of the almost contact structures, which are compatible in a certain sense. We will also add, in the fourth part, we will also consider some metric connections associated to compatible Riemannian metrics in these manifolds. And in particular, we will study the existence of canonical connections with skew torsion in these manifolds. These canonical connections were introduced very recently by Agricola and Dileo, and they fit well in our setting. And if there is some time in the end, I will give a classification in dimension 7 of these almost three contact structures. This seminar will be more algebraic than the previous ones, but in the end, we aim to obtain some geometric results. So we begin by recalling some facts on complex structures on Lie algebras. We will consider a real Lie algebra G and an endomorphism of this Lie algebra, such that the squared is minus the identity, and the following tensor, the Navier-Noise tensor associated to J, which is given by this expression we can see here on top, relating the complex structure and the bracket, is always 0. This says that the complex structure is integrable, and when we left translate it to any Lie group G with this Lie algebra, we will obtain a complex structure, an integrable almost complex structure, and then the Lie group will have a structure of complex manifold where the left translations are holomorphic. Equivalently, the vanishing of this tensor Nj can be seen in the following way. We take the complexification of the Lie algebra. We consider the eigenspaces of this endomorphism J extended C-linearly. The eigenvalues are plus I and minus I. And then the vanishing of this tensor is equivalent to these eigenspaces to be subalgebras, complex subalgebras of this complexification. Okay, but now we move to the case that we are interested in. A complex structure will be called abelian when it satisfies this stronger condition. It's like saying that you see the bracket Jx, Jy is equal to Xy. This means like the bracket is 1, 1 with respect to J. In this case, we have this stronger condition translate when we look at the complexification as the both subalgebras, the eigenspaces of plus I and minus I, are abelian subalgebras of this Lie algebra, and that's why it receives this name, the name abelian. These structures were introduced by Barberis, Dotti, and Miatello. They were looking for some kind of some examples of manifolds equipped with Clifford structures, generalizations of hypercomplex manifolds. Okay, they have had, there are some obstructions for the existence of these structures. For instance, some results of Petrov-Chuk imply that if a real Lie algebra admits such an abelian complex structure, then the Lie algebra has to be two-step solvable. This means that the commutator ideal is abelian. And there are other obstructions. If the codimension of the commutator ideal is 1 and the algebra has dimension greater than 2, then G cannot admit any of these structures. And the center is stable by the complex structure, so it has to be even dimensional. Okay, well, when we add some metric, we obtain some applications to geometry. In particular, they were useful in HKT geometry, hyperKähler with torsion. Let us recall a bit about that. A hyperhermitian manifold is a manifold of dimension multiple of 4, which has a triple of complex structures, and which are related in the following way. They reproduce the laws of the quaternions. J1, J2, and J3 can be thought of as I, J, and K in the quaternions. We also include in the setting a Riemannian metric, which is compatible with all the structures. This means that the complex structures are orthogonal with respect to the metric for any I. And well, this manifold, hyperhermitian manifold, is called hyperKähler with torsion if it admits a metric connection with totally skew-symmetric torsion such that it parallelizes all the complex structures. And also, if we contract the torsion with the metric, you see we obtain a torsion tensor called C, and it has to be a 3-form. So we already know that the torsion is skew-symmetric in X and Y, but we also ask now for the skew-symmetry between Y and Z. And if it exists, it is unique, and it is called the Bismut connection. Let me say something. Each one of these complex structures, together with the metric, admits a Bismut connection. So there is a Bismut connection for J1, another one for J2, and another one for J3. But perhaps it might happen that they are not the same. They do not coincide. When they do coincide is when we have this hyperKähler torsion structure, and it is called the Bismut connection of the whole structure. if this Bismut connection is equal to the Levi-Civita connection, we have a hyperKähler manifold. But I will not talk much about that. We will keep in mind always these manifolds. Now, what is the relation of the Abelian complex structure I mentioned before with this geometry, HKT geometry? We can see that Dotti and Fino prove that if we have a left invariant Abelian hypercomplex structure on a Lie group, Abelian hypercomplex structure means that we have a hypercomplex structure where each single structure is abelian, as defined previously. Then if we have the abelian hypercomplex structure, then any hyperhermitian metric that we add will be HKT. So we have many examples there. And they were able to prove also the converse in the case of a two-step nilpotent Lie group. So if we begin with a two-step nilpotent Lie group endowed with a left invariant HKT structure, then the hypercomplex structure has to be abelian. And this was generalized later by Barberis, Dotti, and Verbitsky in the case of HKT nil manifolds and with any degree of nilpotency. In this case, also the hypercomplex structure has to be abelian. And using these results, Fino and Grancharov, they were able to provide the first examples of compact hypercomplex manifolds which do not admit any HKT metric. So this algebraic notion of abelian complex structure proved to be useful in obtaining a geometric result. So, what is our purpose in this talk or in this work with Julia is to define an analogous notion in the case of almost contact manifolds in the odd dimensional case. So we begin first by recalling some definitions of almost contact metric manifolds. Without the metric part, so we have what is called an almost contact structure. It has to, they happen in a manifold of odd dimension. It's a triple given by endomorphism phi, vector field psi, and one form eta, where phi is an endomorphism of the tangent bundle, and they are related in the following way. Phi squared is minus the identity plus a term involving eta and psi, and eta and psi can evaluate it with 1, the constant function 1. This implies that psi is in the kernel of the tensor phi, and also the image of phi is in the kernel of eta. In this setting, we can split the tangent bundle as a sum of L plus D, where L is a line bundle generated by psi, which is never 0, and D is the kernel of eta, or the one form eta. What I would like to say is you have to think of this as phi is a complex structure on this subbundle D, and you have one extra connection where it is 0. So this is a general definition. Now, then, if M has dimension odd, we take a product with R, it has dimension even, we can define an almost complex structure in the following way. Here we take a vector field of the form, well, X in M and a multiple of the addt in the real line. We define this complex structure using the tensors phi, psi, and eta in this way. And when this complex structure on the product manifold is integrable, the almost contact structure will be called normal. I don't know why the use of these names are used instead of being called integrable. They're called normal, but well, the names come from much before. And one can see this also in a similar way to the complex structure. This is equivalent to the vanishing of this tensor M phi, where this M phi has a bracket of phi phi. This is like the Navier torsion of phi. See here in the last line. And we have to add the term which involves eta and psi. So we will say that the almost contact structure is normal if this tensor is 0, vanishes everywhere. Okay, so we will add now a Riemannian metric. A Riemannian metric, well, we'll have a almost contact metric structure if we have an almost contact structure and a compatible Riemannian metric in this sense. Phi is not orthogonal, but with this equation, we can see that it is skew-symmetric everywhere on M. So we can define the fundamental two form, as always, combining the metric with the structure tensor phi. We obtain a two form, which will be called the fundamental two form. Well, now there are many objects associated to this structure. We have the tensor field phi, the vector field psi, the one form eta, also this form. And so there are a lot of possible classes of this kind of manifolds. If we say that this phi is closed or parallel, or there are certain relations. So I have listed some of them here, but it doesn't matter if you don't remember them, back to the talk. But the most important ones, I'm assuming that the contact structure is normal. The most important ones are in red, the Sasakian, where the phi, the fundamental two form is exact and it is equal to the derivative of the one form. And Kähler, if the one form eta and the two form phi are closed. These are equivalent to being parallel with respect to the Levi-Civita. And there are some other cases, but I don't need to remember all of them. Okay, we move now to the context of Lie groups. I will consider a Lie group endowed with a left invariant, almost contact metric structure, so that we can work at the Lie algebra level, and we will have this structure defined on the Lie algebra. And the first thing we do is to write in terms of the Lie algebra the condition of normality. And okay, normality, remember, is that a complex structure on M times R is integrable, and this is equivalent to the vanishing of certain tensor n sub phi. On a Lie algebra, it is easy to see that this is equivalent to this. The adjoint action of the rep vector psi commutes with phi, and also that there is this relation. This is, and the second condition is like the vanishing of the Navier noise tensor of the complex structure that we obtain when we restrict phi to the kernel of the one form eta. So this is in general. So we will define now what an Abelian almost contact structure is. We will always ask for the first condition to hold, that phi and at psi commute.
What is H in the last?
Sorry, I didn't write. I write it here. It's the complement of psi, is the kernel of the one form eta.
Thanks.
It is written in the next slide. Sorry, I misplaced it. Here it is. I don't know if you see when I put this color here. Okay. The almost complex structure, almost contact structure on the Lie algebra will be called abelian when the action of psi commutes with phi, and we have this. Phi x, phi y is equal to xy when we take x and y in this subspace H. In this case, it is easy to see that the structure is normal, but there is one difference with the complex case that G is not necessarily solvable. We will find examples later where this doesn't happen. So as I said before, well, this I should have said previously, we can write G as the sum of arc psi with H, where H is the kernel of the one form eta. Okay, one example, a very basic example is given by the real Heisenberg Lie algebra of dimension 2n plus 1. So we have a basis given by psi, x1 to n, and y1 to n. The only non-zero brackets are given by this. Xi and yi gives always 2 times psi. And you can define an endomorphism of G, sending this psi to 0 and x to y and y to minus x. So, and eta will be the dual form of psi. It is 1 in psi and 0 on the others. And it is easy to see that this is an abelian almost contact structure. And if moreover we add if we ask this basis to be orthonormal, we will obtain a Sasakian Lie algebra. We will not use that, but I just wanted to include that. But note that this is, in this case, the red vector psi is central. So we will see what happens in general when this vector psi is central. In this case, we can see very easily that the Lie algebra has to be two-step solvable, just as in the case of the abelian complex structure. And we will try to obtain a nice description of these algebras. So we do the following. We write G as the sum of the space generated by psi and H. And I will take two things in H, X and Y. I do the bracket and I take their components, one in psi and one in H, like it is written here. Now, if we take three elements, this in H, and using the psi central, we can write the Jacobi identity for these three elements using the bracket in G. We decompose everything according to this decomposition here, which involves a psi and the bracket in H. And we obtain these two equations. One which involves this bracket sub H, and another one which involves this bracket and this form sigma. The first one says simply that H with this bracket H satisfies the Jacobi identity. So it is in fact a Lie algebra. And the second equation means that sigma is a two-cocycle on the Lie algebra H, that it is a two-form which is closed with respect to the differential in H equipped with this bracket sub H. This can be rephrased simply by saying that G is a one-dimensional central extension of the Lie algebra H by the two-cocycle sigma. And we will write it like this, R sigma plus H with a cocycle here. Note that H is not a subalgebra of G. It has its own Lie algebra structure, but it is not a subalgebra. the brackets are related by the expression here above, which involves also the two cocycle. Okay. But we recall also, I call J the restriction of phi to this subspace H. Oops, what happened here? X is small. Well, but recalling that phi x, phi y is equal to xy, we obtain this. And these two equations, which intertwines J with the bracket H and J with the cocycle sigma, they say that J is an abelian complex structure in the Lie algebra H, and the cocycle is J invariant. And also we can go backwards in the reverse order. If we begin with any Lie algebra, which admits an abelian complex structure, and we have there a J invariant 2 cocycle, we can perform the one-dimensional central extension, and it will carry a natural abelian almost contact structure. So we have a nice description of this, these algebras in the particular case when psi is central. So, what now? Okay, yes. We will move now. I can say more things about this, but I restrict to this because this case with psi center will appear also when we take 3 almost contact structures. Now, I will give the definition of almost 3 contact metric structures. I'm sorry. Okay. We begin with a 4n plus 3 dimensional manifold, M, and it is endowed with 3 almost contact structures. And they are related according to equations which have the name 2 in the slide. They are not easy to remember always, but basically they say that they behave like the quaternions in the intersection of all the kernels of the one forms eta. These manifolds have been much studied lately, and they are quite difficult to study, and they're tricky because of so many possible combinations one can take with these tensors. But they are quite interesting also. Okay, we will say that the manifold is hypernormal if each structure is normal, so that the eigennoise tensor for each phi I is 0. In this case, we can split the tangent bundle in 2 parts. A vertical, this V will be called the vertical subspace. It has rank 3 and it is generated by these vector fields, psi 1 to 3. And the horizontal subspace, in this case, will be the intersection of all the one forms eta, eta 1, eta 2, eta 3. It has rank 4n. And as I said, it's called the horizontal subspace. The other one is the vertical subspace. And it is known that they always admit a compatible Riemannian metric. Compatible in the sense that is compatible with each one of the 3 structures. So it is compatible with phi I for each I. In this case, we will talk about an almost 3 contact metric manifold. In this case, with this metric, both subspace distributions, the horizontal and the vertical, are orthogonal, and the vector fields are orthonormal. The most important class of this is given by the 3 Sasakian manifolds. This means that each structure is Sasakian. There are many results on the topology and geometry of these manifolds, but this is the only time they will appear here, but because they are not compatible with the Lie group structure. I only include them to have some interesting names. Okay, we move now to the Lie group setting. We will consider a Lie group where the with the almost three-contact structure, which is left invariant. Again, we can work at the Lie algebra level. And we will speak of a almost three-contact metric Lie algebra. And we will say that this structure is abelian if for each I, each single almost contact structure is abelian. It's quite naturally similar to the definition of abelian hypercomplex structure I gave before. It happens that they are always hypernormal, and we will call V, Gothic V, to the span of these three rep vectors. And I call H here to the intersection of all the kernel of these forms. It plays a different role as the H Jorge asked about before, because this is codimension 3 now. We can write anyway G as V plus H. Remember that it has dimension 4m plus 3, where V has dimension 3 and H has dimension 4m. One interesting thing about this manifold, this Lie algebra, sorry, is that we can define a sphere of almost contact structures. How do we do that? We have the main ones labeled 1, 2, and 3. Each they are almost contact structures, and we can perform the linear combinations where these coefficients form a vector in the sphere S2 in R3, the unit sphere. So each of these, phi A, psi A, and eta A, gives rise to a almost contact structure on G. It can be seen that if we begin with a almost three-contact Lie algebra, which is hypernormal, then each structure in the sphere is normal. This was proved recently for manifold, more generally, by Capelletti, Montano, De Nicole, Udin in 2016. And the nice feature that we have for these manifolds, even though we will not use this later, but it is nice that we begin with an abelian, almost three-contact structure, then every structure in this sphere is abelian also. So these three structures we began with are, in certain sense, not very important. What is important, more precisely, is the sphere of abelian almost contact structures, but we will not use much of that. We will study now some general properties of these structures. Well, here I have defined, what's the name of this letter? Zeta. Zeta k is the bracket of psi I and psi j, where ijk is an even permutation of 1 to 3. And I have written here, when it is abelian, the almost three-contact structure is abelian, we have some relations which involve the tensors and this zeta k. I don't want you to remember all of them, only there is one that is very important now. It is this. When you evaluate phi I in this zeta I, we obtain the same as phi j in zeta j. And the same happens with k. I didn't write it, but it also happens. So we will put a name to this vector. We will define as z to psi I evaluated in this bracket psi I, which is defined above, where we can put any of the indices there, which they will be the same because of this equation in the box here. This vector is in H, and this vector will be very important in what follows. What time is it? Okay. Why? We can see also that we have a strange property here. number two, but it can be expressed in another way. It means that the form eta R in this bracket of size is equal to 2 times, it's a multiple of the total skew-symmetric symbol, which is 1 if the permutation is even and -1 in another case. And we put the 2 because, well, it was used previously in other works. It is customary, it's a custom to use 2 there. And combining the definition Z of the vector Z and this equation above, we can deduce that this psi I, which is not other thing than this bracket, psi j and psi k, can be written as this sum. The vector Z evaluated with phi I and minus, and 2 times delta this, the vector psi I. So, using this, we can see that if this term involving Z is not there, the bracket of 2 psi's gives me another psi. And that happens. We can see that if we have an abelian almost three-contact structure, then the vertical subspace is a subalgebra if and only if this distinguished vector Z vanishes. And in this case, the vertical subalgebra will be isomorphic to SO3 when delta is different from 0. And it is abelian of dimension 3 if delta vanishes. So we have a useful fact concerning this vector Z. And now we have another lemma with many properties of these structures. It is abelian. And also, I don't want you to remember all of these. These are quite tricky also to deduce because there are so many permutations possible and combination between all these tensors. But we were able to do this. But I only want you to look at the first one here, the one in the box. What happens here? We have brackets with psi I and phi I, and it is the same as evaluating this with the index j. This is x is in the horizontal subspace H. So we can define also a new endomorphism in H. I call it psi, which is defined as the composition of this phi I and the joint action of psi I on H, or in the other way around, because one of the properties that we ask to Abelian contact structure is that they commute. So we have defined another endomorphism that encodes many properties of this structure, and instead of working with the three endomorphism phi I, we can use only one, this psi. So we have a reduction which simplifies all the computations to come. So this is what I say in the first part of this slide. Many properties of the abelian almost three-contact structure are encoded in the vector Z and the endomorphism psi of the subspace H. Moreover, they are related by the following fact. The vector Z is always in the kernel of psi. Recall that Z is in H. And if we evaluate it, we can see that it gives always 0. In particular, this means that if we make the bracket between Z and any element in the vertical subspace, it is 0. So we know the adjoint action of Z on the vertical subspace. What happens? What can we say about the adjoint action of Z on H? And this also doing a lot of computation, combining all the possible indices, we obtain the adjoint action of Z on H is given by this operator. twice phi squared plus delta phi. For reasons that will become apparent later, it is interesting to know what happens when psi is invertible endomorphism of H. And if it is invertible according to the proposition, Z has to be 0. So V is a subalgebra of G, the vertical subspace. And if Z is 0, we have that this joint action is 0, so this endomorphism has to vanish. And since it is invertible, we have that psi has to be minus delta times the identity operator on H. So it is a quite easy description of this operator. Also, it will be of interest to know when the vertical subspace is contained in the center of the Lie algebra. And if we reproduce the same computations as we did before in the case of only one abelian almost contact structure, we can see that in this case, G will be also a central extension of the horizontal subspace, but this time it will be a three-dimensional central extension. So H, this means that H, the horizontal subspace, which admits a Lie bracket, which we call bracket sub H, which does not make it a subalgebra of H, it's another bracket. The restrictions of the endomorphism phi I, which I call Ji, give rise to an abelian hypercomplex structure on H. And theta is a V-valued 2 cocycle on H, which is invariant by all the complex structures, Ji. This means that we can write theta as a combination of 3 usual 2 cocycles on H, which are closed with the differential of H. And all of these 2 cocycles are Ji invariant. So we also have a nice description of this kind of Lie algebras when the vertical subspace is central. And this process obviously can be reversed. We begin with a Lie algebra with an abelian hypercomplex structure and R3 valued 2 cocycle on H, which is invariant by the hypercomplex structure, and when we can perform the central extension, and it will admit a natural abelian almost three contact structure. Now the name is too long to say that every time, but well, I cannot say anything better. Abelian almost three contact structure. Okay. Well, now I begin. I believe. Some examples, let me show you. Well, I will not show you, I will only tell you, and you must believe that there are examples of this. These are examples where of abelian almost three contact metric structures on the algebras, where the vertical subspace is central, and they are quite well known. For instance, we can take the quaternionic Heisenberg group, which has dimension 4n plus 3. Then we can also take a product of the complex Heisenberg group of real dimension 4n plus 2 with R. This will also admit the structure that we are interested in. And also we can take a product of the real Heisenberg group of real dimension 4n plus 1 and multiply by R2. This will also admit such a structure. And they are all central extensions of the abelian Lie algebra of dimension 4n by R3 using a suitable 2 cocycle there. I do not want to give you the description, but keep in mind that they do exist. And these are quite famous names, and they have appeared many times in the study of the almost three contact manifolds, these groups. Okay, so what do we do now? I move now to a more geometric setting. We will recall that the metric connection with skew-symmetric torsion is a metric connection on a Riemannian manifold, where the contraction, where this tensor, which is obtained contracting the torsion with the metric, is skew-symmetric. Then, as the Bismut connection I talked about in the first slides, this connection and the Levi-Civita connection are related by this form. You obtain nabla by adding to nabla G the 1/2 of the torsion. And it is very well known that they have the same geodesics. When nabla has parallel torsion, this is another extra property which makes it even a better connection. There are more symmetries. For instance, we have this symmetry in pairs, like you can see here. X, Y, and Z, W can be interchanged. And the Ricci tensor associated to nabla is symmetric, which is equivalent to the torsion form being co-closed. And the second Bianchi identity holds. Okay, and very recently, it is quite difficult to define a good metric connection with skew-symmetric torsion in the setting of almost three-contact metric structures. There are some cases in 7 dimensions or some other connections, but there are many possibilities. I will talk about the canonical connections introduced by Agricola and Dileo very recently on an almost three-contact metric manifold. Such a connection, a metric connection with skew torsion, will be called canonical if there exists a smooth function satisfying this formula here that you see in the box. It says what the derivative, the covariant derivative of the tensor phi I is. It is related to the other tensors, and it is multiplied by this function beta. One can compute, if this connection exists, it is unique, and its torsion, it is unique, satisfying this equation here, and its torsion is given by these equations, where delta is a differentiable function, which appears down here. It's related to the number that we saw previously. Here it can be a function. If we have the first equation, we know also how to derive the other tensors, the rep vectors and the one forms eta, and they have the same form as the previous one, and the beta function appears in all of them. So this connection will be called parallel if beta is 0, because all of the tensors will be parallel. Okay? And the existence of nabla is equivalent to this series of conditions, but they are quite complicated to describe now. I will only say that using this, we can see when such a connection exists on the setting of Abelian almost three-contact structures. I will skip this, and I go back to the Lie groups with a left invariant almost three-contact metric structure. We will say that it is parallel canonical if any Lie group with the left invariant corresponding structure is also parallel canonical. Okay? So, we will be more precise next in the following result, and we will consider what happens when this structure on the Lie group is abelian. And in this case, well, we have a lot of information, but the most important ones are these points 1 or 2. This structure is canonical if and only if V, the vertical subspace, is a subalgebra, and the brackets of the rep vectors is given by this, with this number delta. And there is a relation between the conduction psi I and phi I using the number beta, which appears in the definition of the canonical connection. We have also the description of the torsion free form, which is in terms of the tensors eta and the numbers beta and delta, and C is a free form defined this way, only on H. And this is the same expression as the Bismut connection on a Abelian hypercomplex Lie group. So we will investigate more this, and we can see that these conditions are equivalent to the following. First, since V is a algebra, this is equivalent to the vector Z being 0, and the endomorphism psi being equal to a multiple of the identity, multiple involving beta. Okay. And we will consider different cases according to beta equal to 0 or different from 0. So we distinguish the cases parallel and non-parallel. We begin with the parallel case. This means that Z is 0 and the endomorphism psi is 0 because beta is 0. We have these two possibilities. You can see them here in this setting. And then what happens when delta is 0, so that the vertical subspace is a Abelian subalgebra? In this, we can see that, in fact, it is contained in the center of the Lie algebra. And as we saw before, G is a central extension of this form with a suitable cocycle, and H an Abelian hypercomplex Lie algebra. Then this finishes the case, delta equal to 0, and when delta is not 0, we can prove that both subspaces, the vertical and the horizontal one, are ideals, and so G is isomorphic to SO3 times an Abelian hypercomplex Lie algebra. In the first case, in this, when delta is 0, and we have the V is central and G is it's a central extension, the torsion takes this particular form. There is a nice expression to compute the canonical connection. On the Lie algebra H, it coincides with the Bismut connection. And we can give an equivalent condition for T being parallel. It is given there. And well, I do not want to talk more about this, but there are examples of this. Here, the product of the real Heisenberg group times R2 will have one of these connections, and moreover, it has parallel torsion. In the other cases, with the complex and quaternionic Heisenberg groups, they will have parallel canonical connections, but the torsion will not be parallel. All of these are nilpotent, and they admit co-compact discrete subgroups. And oops, it's almost time, but I will move a little forward. In the case when Z is 0, psi is 0, but delta is not 0, I said that both are subspaces are ideals. In this case, the torsion free form takes this form. We can also compute explicitly, and the canonical connection are related to the Bismut connection. And we can see that the torsion is parallel if and only if the Bismut connection H has parallel torsion. And an example of this is SU2 cross this product of the real Heisenberg group with R3. This Nilpotent Lie group in the parentheses are the only ones that I know that admit abelian hypercomplex structure with Bismut connection with parallel torsion. I have no idea if there are any others I haven't found. If anybody knows one, please tell me. And these groups admit also co-compact discrete subgroups, taking a finite subgroup of SU2 and any lattice here in this group. And okay. Do I have some more minutes, Jorge?
Yeah, 2 or 3.
2 or 3, okay. Let me finish with this. In this case, we will talk about the non-parallel case. This means that the endomorphism psi is equal to minus beta mod 2 times the identity. In this case, the vertical subspace is a subalgebra, even with these brackets for some delta. We can see that beta and delta are related by beta equal to 2 times delta, and therefore V will be isomorphic to SO3 because this number delta is non-zero. H is an abelian ideal, and the non-zero brackets are given by this. These are the ones as before, and the red vectors act as the multiplication by the tensor phi I. So we can say that G is a semi-direct product of SO3 and R to the 4n, where the action of SO3 in R4n is given by a hypercomplex structure. And in this case, as I said before, beta is different from 0, so the canonical connection will not be parallel. But anyway, it is quite nice because the torsion here takes this form, and we can see that the torsion is parallel. So we have a nice, even if it's not parallel, it's a very nice metric connection with this skew-symmetric torsion. Okay, and we have the examples are given. I will not say much about this. The associated Lie groups simply connected is the semi-direct product of SU2 with R4n using the multiplication of the quaternion numbers. I will not say much now because I do not have much time, but I think this is quite nice, and we can produce co-compact discrete subgroups here using certain integer matrices. We can produce these examples. Many of these examples you can see here are of the form a cyclic subgroup, a finite subgroup in SU2 of order m for m equal to 2, 3, 4, 6, acting on a certain lattice in R4. And then we can extend this to any dimension for n. I will not say much about this, but it is very interesting. And there are other, these are not the only co-compact discrete subgroups we can produce. We can take also, for instance, the quaternionic group Q8 and take the semi-direct product with the standard lattice in R4n, and this will provide also a co-compact discrete subgroup. And all these structures descend to the quotient, so we have many compact examples of this Lie algebra. So with this Lie group, or this Lie algebra, or this Lie group, we can produce several different lattices, and they will give rise to many different non-homeomorphic manifolds admitting canonical connections. Well, I had also the classification in dimension 7, but I will skip that, and I only have one more slide, which is this. Thank you very much for your attention. So I should stop the presentation.
Okay.
Okay.
Thank you very much for
I don't know if I was too fast, but I hope that you have followed me.
we were here. Is there any question? Okay, Enrique.
So I typed the question during the talk. I was just wondering, what's the symmetry group for these almost three contact structures? Some SP sitting inside UN, right? What's the symmetry group? What's the stabilizer of your model?
Yes, it's a SPN plus something. I don't remember very well, but yes, there is an SPN and a U1, I believe. Or
Yeah, there's a
yes.
I was just wondering. So when your torsion is parallel, that's already too much.
Yes, there is a
Strong, yeah.
there is a reduction there, a strong reduction.
Right. So did you stop and wonder what it would mean for these structures to be harmonic?
Not yet, not really.
I might
But it will be very interesting. Yes,
be able to tell you.
Okay, yes, I'm very interested in continuing studying this. This is still an ongoing project. We have not finished this, and we will upload this to archive very soon. But there are, I think, a lot of still interesting questions to be studied, and this is a possibility for the harmonic structures.
Right.
Okay.
Thanks.
Thank you.
Any other question or remark? Okay, if not, let's thank again.
Okay. Thank you.